Okay, in this section, let's prove the last important theorem in this section, the maximum modulus theorem. The maximum modulus. Okay, maximum modulus. So what is it? The statement is the following. If G is a region and F from G to C is an analytic function such that there is a point A in G with absolute value of f of A is greater than or equal to the modulus of f of Z for all Z in G. If this happens, then this f is constant. F is a constant. Okay, so it's a very interesting property because we don't have such property in the calculus. How do we know we don't have such in the calculus? For example, we have fx equal to, let's just choose x squared minus 9. We only choose region, connected open, -3, +3. If we check the graph, it will be like this, right? And the maximum of the modulus of fx is equal to modulus is equal to 9 at x equal to 0, right? So when x is equal to 0, you get a negative 9. Put the ups value is a positive 9. This is a maximum modulus. But this function is not a constant function, right? In the calculus, we can reach the maximum ups value inside the domain, But the complex analysis just say that's impossible if you don't want the constant function. Constant function, of course, it reaches a maximum modulus everywhere, right? So it says if it's not constant, it cannot happen like this. Okay, now let's see. Assume we have such A. So A is an interior point. Then you choose a sufficiently small r and take the closure. It will be inside G. Okay, so you choose a small enough r. And we take the closure because we want to include the boundary. So gamma of t is A plus REIT for t in 0 to 2 pi. Okay, so you do have a circle. Okay, then by the proposition 2.6, by proposition 2.6, we get f of A is equal to 1 over 2 pi I integral along gamma f of W over W minus A dW, right? Actually, the 2.6, this is Z. Z is inside the open disk. Inside the open disk. For arbitrary point inside the open disk, we have such integral. Of course, the center is inside the disk, so we just especially apply it to the center. We apply the 2.6 to the center. To the center, we apply to the center, we have advantage. Remember this W is A plus REIT. This is a smooth curve, so W minus A is REIT. dW is REIT times I and dt. Okay, remember we have such concrete parameterization, so it's equal to 1 over 2 pi I integral gamma. Gamma, if we use t, parameter t, it's from 0 to 2 pi. And here f a plus REIT, this is W. And the W minus A is REIT. dW is REIT. I dt. Right? So we cancel this denominator with this denominator, cancel I with this I. So we have 1 over 2 pi integral from 0 to 2 pi f a plus REIT dt. Both factors are cancelled. Alright, so this is the special case when the point Z is selected to be the center. If you just have a random Z inside the disk, we cannot get such formula. Okay, so now let's see. FA. Let's check its ops value. Ops value is equal to 1 over 2 pi integral 0 to pi FA plus REIT dt. Right? We just put ops value directly. And then we are going to move this into the integral. If we move it into the integral, we have a inequality. Integral from 2 pi ops value f a plus REIT ops value and dt. Okay, just put this integral into put this modulus into the integral. And well, this is arbitrary point. By the condition, arbitrary point has modulus less than or equal to FA. So we are going to put FA, modulus of FA, right? And this is a constant. You integrate the constant along 2 pi. It's a constant times 2 pi. And times 1 over 2 pi. This is equal to the modulus of FA. All right? So you start from the modulus of FA less than or equal to this quantity and less than or equal to modulus of FA. What do you get? You get this one is equal to, by the squeeze theorem, this quantity is equal to the first one, is also equal to the third one. All right, and when we have such equality, remember this is constant number. We can get this integral is equal to 0. How do we get this integral? You multiply this two sides by 2 pi. You will cancel this 1 over 2 pi, and here it becomes 2 pi times this one, times this expression. And then you write 2 pi as an integral from 0 to 2 pi. It's a constant, so it's equal to it. And then you move the right term to the left term. Right? So anyway, you will have such integral. This is the calculus. This is a non-negative number. You integrate a non-negative number equal to 0. Then it implies that this non-negative number has to be 0. Of course, it's continuous. We need the continuous condition. Okay, for all t in 2 pi. Okay, so we have this. Well, check here. This equality comes from this computation of inequality and the square theorem and the integral of continuous non-negative functions equal to 0. Eventually we got this. And this works for all r greater than 0 and bar contained in G. So basically you have a small disk and you can shrink this you can shrink well, let's not say this way. It works for all radius less than r, because r we already select r. So it works for all radii. I think it's the plural is a radii. Yeah, it works for all radii less than r. All radii less than r, it can shrink to 0. So hence we get for any z in bar, for any z in bar, modulus fa is equal to the modulus fz. This is on the circle. You shrink the circle, you will occupy the whole disk. Right? So you will cover whole disk. So now what we have? We have function f from bar to C with fz modulus equal to a constant. Okay, so that's a condition we can get so far, the information we have so far. So we're going to prove the analytic function with this property will be a constant function. How do we know it's a constant? Actually, it was an exercise in the chapter 3. So the exercise. This is chapter 3, exercise 3.17. But now let's discuss this exercise. Okay, so analytic function is uz plus ivz. In chapter 3, we don't have a lot of tools. We only have limited information. Okay, uz is fz is uz plus ivz, uxy vxy, and they have the Riemann Cauchy-Riemann equation. Cauchy-Riemann equation. The ux is vy, vx is negative uy. Okay, CR equation. And the modulus of fz is a constant, so it means u square plus v square is equal to k square. U square plus v square is equal to k square. This is constant. uv are functions. Then we differentiate two sides with respect to x. So 2 partial u partial x, u plus 2 partial v partial x, v is equal to 0. All right, and then we differentiate this also with respect to y. 2 partial u partial y v u plus 2 partial v partial y v is equal to 0. Just partial differentiation. And then we check, I'm going to change partial v partial x to be negative partial u partial y. 2 cancel, so we will have ux u minus uy v is equal to 0. And this is uy u vy v partial y is ux plus ux v is equal to 0. All right, just apply the CR equation, Cauchy-Riemann equation. Okay, so any place you think I'm too fast, you just pause the video. You can or repeat it. Okay, so I just replace this and replace this one, and of course I cancel the 2. And next I'm going to multiply this equation by u and this equation by v. The first equation you multiply by u is a ux u squared minus uy uv is equal to 0. The second equation multiplied by v, you get uy uv plus ux v squared is equal to 0. Okay, and we're going to add them together. Uy uv, here's negative, here's positive, cancelled. You will get ux u squared plus ux v squared is equal to 0. Add both, add these two equations, and then you have ux u squared plus v squared is equal to 0, and u squared plus v squared is k squared, of course non-zero. So it's a ux k squared is equal to 0, so we get ux is 0. Okay, so this is one condition. So far we get ux is 0, ux is 0, vy is 0, partial v partial y is 0. And for the other part, this one, we got this ux by multiplying the first by u and second by v. Let's change it a little bit. We multiply the first, let me copy, multiply the first by negative v, okay, negative v. I want to make this symbol positive, this sign positive. Uy v squared is equal to 0. And this one we're going to multiply it by positive u. So you get uy u squared plus ux uv. So this is the first one. And second one, this is multiplied by negative v. This is by positive u, the second one. Okay, we have this. And then we add these two equations. You will cancel negative ux uv from the negative ux uv. So you will get uy u squared plus v squared is uy times u squared plus v squared equal to 0. Then you will get uy is equal to 0. Uy is 0, vx is 0. Ux, uy, vx, vy are all 0. So uv are constants. uv are constants, f is constant. So we do prove that f is a constant function over the disk. It's a constant function over disk. It will be a constant function over the whole domain because you will have a limit point, right? The disk. when it is a constant function if there's a limit point, a sequence with a limit point, so that the function is always at constant. Correct? If check this with a theorem 3.7. Theorem 3.7. All right. So we proved the maximum modulus theorem. The proof is not crazy. The proof is not crazy. You first verify that the function must take the constant modulus. After you get a constant modulus, this is one of our independent practice. This is one of independent practice. If an analytic function take the modulus constant, then it has to be a constant function. All right. Okay, so in this part, the exercise, you can try that on page 80, page 80, exercise 1. Exercise 6. Eight. And 9. Try them, see if you can do it. Okay, so this is the section 3, zeros of analytic function. Very good. So in this section we have an important theorem, the maximum modulus theorem, the MMT, and we also have the Liouville theorem. Bounded entire function is a constant. MMT is about constant, and the fundamental theorem algebra, which is the corollary of the Liouville theorem. All right. Okay, so next, let's talk about section 4. The index of a closed curve. Index of closed curve. Remember that assume we have gamma t equal to a plus REI NT. Let's check EINT. T is between 0 and 2 pi. If you don't want to use this, you can put the t is between 0 and 2n pi. Yeah, let's 2n pi. Okay, EIT, but t is between 0 and 2n pi. You'll get this round several times, n times, and we integrate this 1 over z minus a. 1 over z minus a is the center, dz. Okay, so 0 to n pi 1. Z is on the curve, on the circle. So z minus a is REIT. dz becomes REIT times I and times dt. Correct? And you cancel this, you will have constant function r. Constant function I integrated along 0 to n pi is 2n pi I. 2n pi I. Right? So it's a very quick computation. And this section will tell us this kind of a computation, especially this result, is not a special result only for such gamma. It actually works for many gamma, many curve path. So that's a theorem 4.1 proposition. If gamma from 0, 1 to C is a closed rectifiable curve, and A does not belong to the trace of gamma. A does not belong to the trace of gamma because we want to make Z minus A. Z minus A, it cannot be 0, so that's a purpose. Then 1 over 2 pi I, 1 over 2 pi I, if you divide by 2 pi I, you will get n. So n is integer. 1 over 2 pi I times the integral along gamma dz over Z minus A. dz over Z minus A. This one is an integer. This is an integer. So you see here, for arbitrary closed rectifiable curve and any point of this curve, this integral is always 2n pi I for some n. Right? So this just means our computation, even though we use a special parameterization, but it's not that special. Okay, now let's prove it. We want to show it's an integer here, but gamma is a closed rectifiable curve. We're going to just show this theorem under the hypothesis that gamma is smooth. If gamma is not smooth, you use a piecewise smooth polygonal path to approximate it, and you will still get an integer. Okay, polygonal path to approximate. Okay, so we only show the proposition by assuming gamma smooth. Okay, gamma smooth, we can dz is d gamma, it's a gamma prime, right? So we define, so this one is a parameterized, the normalized gamma. It's from 0 to 1 always. Here, if we want to 0 to 1, then this place will be 2n pi it, 2n pi it, 2n pi it, and then t is between 0 and 1. Yes. If we write this way, here we write this way, then t is between 0 and 1. It's just normalization. Okay, so we define a g from 0, 1 to c by, it's very constructive, it's a very surprising proof, because the first time it looks very confusing. Okay, this is t, not, it's a t. All right, so we actually get part of this stuff. We get a part of this stuff. We don't get the whole thing. Whole thing is from 0 to 1. Here we get a 0 to t. Okay, and this gamma prime s over gamma s minus a is exactly dz over z minus a. That's the same thing. Only change is this integral part. And we're going to show should be 2n pi I, right? 2n pi I. So we know what? G of 0 G of 0 is 0. Integral from 0 to 0 is just 0. From a to a, integral 0. G of 1. G of 1 is this what we want to present along gamma. G of 1 is this. Okay. And what is G prime? G prime of t by what? By the fundamental theorem of calculus, we know it's a gamma prime of t over gamma t minus a. Just evaluate this integrand at t, my bad. At t, you get this. Right? So let's see the magic. The magic is the next one. So we have exponential negative g gamma minus a. This one is a differentiable function. This composite function is also a differentiable function. And we are going to differentiate with respect to t. Okay, so now let's see the product rule, chain rule. So e negative g times negative g prime of t. This is the chain rule here, product, the first term, and second plus e negative g gamma prime of t. Okay, that's product rule. E negative g. G prime is this. So this is a negative g prime gamma prime of t over gamma minus a times gamma minus a and plus e negative g gamma prime of t. If you cancel denominator with denominator, you have negative sign here, have positive sign, the sum is 0. Alright, this differentiable function has derivative constantly 0. So e negative g gamma minus a is constant. It's a constant function. Constant function, well, let's see. Constant function, we get e negative g of 0 gamma 0 minus a is equal to e negative g of 1 gamma 1 minus a. G0, what is G0? G0 is 0. E to negative 0 is 1, so this is gamma of 0 minus a. G1, I don't know what the G1 is. I'm looking for G1, so G1. Gamma 1. Gamma 1, it's a closed, where is it? Closed curve. Remember, it's a closed. Closed, we got gamma 0 is equal to gamma 1. And remember, a is off the trace. Off the trace, gamma 1, gamma 0 minus a is not equal to 0. This is non-zero, this is non-zero, they equal to each other, so you get 1 is equal to e to negative g1. E to negative g1 is 1. What do you have? We have g1 is 2n pi I for some n, for some integer n. I don't know what that integer is, but for some n. And then we are done. Right? We are looking for this. We are looking for the proof for the integer n. This integer, if you divide by 2 pi I, you get n. And we are done. You see, this proof is a very, very constructive, and while no one could expect such smart construction, but once the other people invented it, we just try to handle and try to use this trick. Okay, excellent. So we finished the video, and we will continue the discussion in the next video. Thank you very much.